So today we're going to take a look at changing temperature and state, so using the specific heat capacity and the specific latent heat equations in conjunction with each other. So I hope this graph gets burned into your memory, this temperature versus time graph for heating a pure substance. And while we do that, we assume that energy that we're supplying is either going into raising the temperature, giving us a straight line, or into breaking the bonds or changing the state, giving us a horizontal line on our graph, and then raising the temperature, breaking the bonds, raising the temperature, and never both of those simultaneously. Now, realistically, what really happens is this solid does heat up, and then when it gets close to its melting point, some of the particles have enough energy to start to break bonds and become a liquid, and some of the particles are still gaining kinetic energy to get up to the melting point temperature. So there is technically a little curve here where some particles are breaking bonds and some particles are gaining kinetic energy. But that curve is so small that we can approximate it as two straight lines. We can make a good model of it, and that's what physics is about, finding good models. So on our graph, we see this as straight line, straight line, straight line, straight line, straight line, and they're discontinuous at these points. Similarly, when we deal with this mathematically, we deal with this section, and then 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 we deal with this section. We deal with them separately. So we've already dealt with these two equations, changing temperature, Q equals mc delta theta, and changing state, Q equals ml. Now notice that both of them have a Q. That is the energy added for both of those equations. Both of them have an M. That is the mass for both of those equations, the mass of the system that we're dealing with. C is our specific heat capacity of our system, and delta theta is the temperature change, remember final minus initial, that system is undergoing. And on this side we've got L, which is the specific latent heat. Remember, we need to specify whether it's of fusion, solid to liquid or liquid to solid, or if it's the specific latent heat of vaporization, liquid to gas, gas to liquid, because that will change the number. Now, when you get a question that involves both of them, you want to break down what's happening into either changing temperature or changing state, and write yourself a little list of what's happening and in what order. Then do those calculations on your list as if they're separate things. At the end, you can add up your energy answers to get a total energy. And when you're doing this, use words, use subscripts, use titles, use headings in your answer to describe to your examiner what's happening and what you're doing. Now, I would recommend that you don't make a note on this right now, that we try an example together, and then you come back and you make like a little how-to note, or you annotate your example. Alright, so here's the example that we did incorrectly. It was to spot my mistake when we were learning about specific heat capacity. I want you to have a go and see if you can do it now. You should be able to. It does have multiple steps. Make sure you're using headings and whatnot to show your work and explain to the examiner what you're doing and how you're going through it. So pause the video now and give that question a try. Alright, so there's not a lot of space on this slide, so what I'm going to do is I'm going to read through the question and grab the relevant information, and then we'll go to like a fresh slate so that we can do the solution. How much heat is required to bring 1 litre of water, so that's our volume, 1 litre, and usually we use meters cubed, initially at 75 degrees Celsius, to 120 degrees Celsius. The density of water at 75 degrees Celsius is 975 kilograms per cubic meter. Now the other thing that we're going to need is the specific latent heat of vaporization. We're going from liquid water to water vapor or gas. So our specific latent heat of vaporization of water is 2300 kilojoules per kilogram. And we're also going to need the specific heat capacity of water because we're heating up the water, and of steam because we're heating up steam. So I'm going to use some subscripts for that. So specific heat capacity of W for water is 4181 joules per kilogram per Kelvin. And for steam or water vapor, so we'll go S for steam, is 1996 joules per kilogram per Kelvin. Alright, so here's all the information that we know that we got down from the question. And the first thing that we realise we need to do is we need to find out our mass. We know that density is mass per unit volume. So our mass is going to be our density times our volume. So our mass is 975, there should be a minus 7, times 0.001 or 0.975 kilograms. So we're just going to put that into our known column. So we can clear out this space. Right, so now we need to make ourselves a little list. What's going on? Well, the first thing that happens is that water goes from 75 degrees Celsius to 100 degrees Celsius. And then the water evaporates or boils. We can say boils at this stage because it is at the boiling point. And then the steam goes from 100 degrees Celsius to 120 degrees Celsius. And these are the three different calculations that we need to do. So whether you write yourself a little list of what you're doing or whether you use sort of headings or subscripts, completely up to you, but make sure it's really, really evident to your examiner what you're doing and where you're doing it. So the first one, heating up the water, we want to use heating up, Q equals mc delta theta. And be careful with this because our delta theta here, even though we put final minus initial, is not our total final and our total initial. It's the final and initial for our water, so just the 75 to 100. So when we substitute our numbers in here, we've got the mass times our specific heat capacity of water. This one we're specifically looking at the water being heated up. So 4181 times our final minus initial temperature. If we plug all of that into our calculator, we should end up with 101,911.875, and then we need to be careful about our units here. So this here is mass, that's in kilograms. This is our temperature. Remember, it's a change in temperature, so degrees Celsius is absolutely fine. This specific heat capacity that we used is in joules. So this answer here is also in joules. Now, that's a ridiculous number of joules, and we're probably better off converting that into kilojoules. And now, for the moment, it's okay that we've got a lot of extra decimal places and whatnot, because we're just dealing with intermediate values, so we're not rounding to an appropriate number of significant figures at this point. And if you wanted to, make it a little bit more prevalent to your examiner what you're doing, you could even call this like QA, because this is the heat for what we've labeled as section A. So this answer here, I'm just going to move up to here so that we can get rid of this and use this space again. So 101.9 kilojoules. All right, and then the next thing we have to deal with is this water evaporating, which we've labeled part B. And when we deal with a changing state, we use Q equals ml, and plugging those in, the mass is 0.975 kilograms, and the specific latent heat of vaporization of water is 2300. And so when we plug that into our calculator, we get 224 2.5. And again, being really careful with units. So we've got kilograms, and our specific latent heat is actually given in kilojoules. So this answer is already in kilojoules. It takes a lot of energy to boil water or evaporate water. And again, I'm just going to move this answer back up here so that we've got this space again. So QB is 2242.5 kilojoules. And then we need to take a look at what we've labelled as part C, or heating up the steam. And again, it's a temperature change, so we want to use Q equals mc delta theta. And when we're using this, our final and initial temperatures, again, aren't the final and initial temperatures given in the question. They relate back to the steam increasing in temperature. So the mass of steam is 0.975, and our specific heat capacity, remember, we're dealing with the steam and not the water anymore. We're dealing with water vapor. So we use 1996 as our specific heat capacity, and then this temperature change is the temperature change of the steam, so 120 as a final and 100 as an initial. And then we can put all of this into our calculator, and we should end up with 38922. Again, be careful with units. We've got kilograms, we've got degrees Celsius, but it's a change in temperature, so that's okay. And our specific heat capacity is in joules. So this answer here is also in joules. So if we wanted to put it into kilojoules, we'd have 38.9 kilojoules. And again, we're just going to move that up so that we've got a little bit more space. So QC is equal to 38.9 kilojoules. Now, the total energy that's required is the energy required to heat the water from 75 degrees Celsius to its boiling point, 100 degrees, plus the energy required for the state change of liquid to gas water, plus the energy required to increase the temperature of the water vapor from 100 to 120 degrees. So we can then add those all up. And the other thing that you want to double check is that all of these are in the same units, whether it's joules or kilojoules, they're all in the same sort of like prefix to that unit. Because if we had joules and kilojoules and joules, and you just add up the numbers, that's not going to work. So do double check that they are in the same prefix. So we've got 101.9 kilojoules plus 2242.5 kilojoules plus 38.9 kilojoules. And all totaled, this should be 2383.3 kilojoules. Now we can start thinking about significant figures and how many we should have and whatnot. So realistically, this volume here is to 1, but we never ever round to one significant figure. Our exam would probably tell us something like 1.00 litres, just to give us some extra significant figures there. So because of this temperature here, we should probably round to 2 because it's 75 and not 75.0. If your exam had 75.0, then you'd want to make sure that you're rounding to 3 significant figures. So to 2 significant figures, this is 2400 kilojoules. And if you would rather write this as 2.4 megajoules, that's quite all right. Now, 2.4 megajoules is a massive amount of energy, and that's just the amount of energy it takes to heat up really hot water and turn it into relatively cool steam. To give you an idea of how big of a number this amount of energy really is, imagine an absolutely massive lorry filled to the brim, like one of the really big ones that you see. Now, legally in the UK, the largest mass of lorry that's allowed on the roads is 44 tons or 44,000 kilograms. So let's say, it's a little bit under that maximum weight and it's 40,000 kilograms. So we're taking the biggest lorry that you can possibly imagine that's driving down UK roads and filling it absolutely to the brim so that, much more, and it's not allowed to legally drive down the road. This amount of energy, this 2.4 megajoules, would be that lorry driving down the road at 25 miles an hour. Now, 25 miles an hour doesn't sound like much, but it's a massive lorry driving at 25 miles an hour. That would be like a massive lorry driving past your house in the residential area. You would definitely never step out in front of that. If all of that kinetic energy was transferred to you, you would be dead, easily dead. But that's how much energy heating a little bit of water takes. Water takes loads of energy to heat up, absolutely loads of energy to heat up. So if we could take that massive lorry, that 40-ton lorry, driving down a residential road and convert all of its kinetic energy into energy inside a litre of water, which is probably about the amount of water that you put in your kettle, all it would do is take that 75 degrees Celsius water, heat it up to 100, convert it to steam, and only manage to get it to 120 degrees Celsius. That is a lot of energy. Now, I realised today was essentially just a question, like an example for you to do, but a lot actually comes out from this, and how you want to get this into your notes, whether it's by making annotations of your work or by creating an entirely new note, completely up to you. So like the past few videos, we model heating substances as increasing temperature or changing state separately. Mathematically, we deal with these separately, so we can either change temperature, where we use Q equals mc delta theta, or we can change state, where we use Q equals ml. When you're combining these, do be careful with units. Like we saw in our example, we had to put everything into either joules or kilojoules. We chose kilojoules because it made more sense, but we could have equivalently put everything into joules. Just make sure that when you add them up, they are all in the same unit. And as a final point, use headings or subscripts or titles or words inside your solution to clearly communicate to your examiner what you are doing. They shouldn't be doing any work or any thinking. It's all down to what you write. Have a fantastic day.